planets with hydrogen-rich atmospheres could harbor life. Lab experiments show that yeast and E. coli survive and reproduce in hydrogen-rich conditions. This is an article by Lisa Grossman, who is an astronomer and writer from Boston, who looked at an article and study in the science journal Nature about how microbes could exist on planets that are rich in hydrogen in their atmosphere. This being a artist's rendition of what that would look like, possibly. The author goes on to explain and use comments from the lead scientist of the study, Sarah Seeger, in the science journal Nature from MIT, that they're trying to expand people's view of what should be considered a habitable planet, and they want to see what the chances are that we might find life elsewhere. Seeger and her colleagues placed yeast and E. coli, both considered stand-ins for other single-celled organisms, so a fungus and a single-celled bacterium, in small bottles with some nutrient broth. That broth probably has simple carbohydrates, amino acids for protein building to support life. The researchers displaced the air in 6 bottles and placed it with pure hydrogen gas, 100% pure helium gas, or a mixture of 80% nitrogen and 20% carbon dioxide, so similar to our atmosphere, except you exchange 20% carbon dioxide for the 20% oxygen that is in our atmosphere on Earth. And then a final set of bottles was left with Earth air, that being the control, right? Every few hours, the researchers removed some of the microbes with a hypodermic needle to count how many were alive. The microbes had replicated in every atmosphere tested, the team reports May 4th in Nature Astronomy. But were the rates the same? Is kind of what I would want to know. In addition, E. coli in particular produce several gases that already are considered potential biosignatures, or, as Grossman goes on to say, signs of possible life if found in other planets' atmospheres, that including ammonia, methanethiol, and nitrous oxide. E. coli is such a simple organism, yet it produces an incredible array of gases, says astrobiologist Giada Arney of NASA's Goddard Space Flight Center in Greenbelt, Maryland, who was not involved in the experiment, so they're taking on additional points of view of other scientists. Knowing which gases can be produced by life is a necessary first step towards vetting them, establishing them as possible detected biosignatures on an exoplanet. So using these as a way to figure out if an exoplanet has life or potential for life on that planet. Again, the James Webb Telescope, being able to look at the spectra of sunlight passing through a planet's atmosphere, going to be really important. Or this is going to become really important in looking at that spectra to figure out what's in the atmosphere. But just seeking a hydrogen-rich atmosphere isn't enough, says astrobiologist. Biologist amongst the stars. Pretty cool job. John Burroughs of the University of Washington, Seattle. Again, another scientist's point of view. A planet would also need to have the equivalent of the nutrient broth in the bottle for life to survive. That's a good point. Perhaps a liquid water ocean exchanges chemicals with a rocky surface. So you need those amino acids, you need those minerals like salt, sodium chloride, and you need carbohydrates to be present, or a way to create those carbohydrates. Astrobiologists plan to search for signs of alien life by looking at starlight filtering through exoplanets' atmospheres. If life on a rocky planet's surface emits telltale gases, those signatures, like methane and ammonia, future telescopes like the James Webb Telescope would detect those emissions. And that's what I've been saying, is that if you could find these gases in the spectra as it transits in front of its star, you could determine if these gases are done by life, if the planet has life or a potential for life. It's not clear whether rocky planets with pure hydrogen atmospheres exist. Based on what's known about how planets form, pure hydrogen atmospheres should be rare, says planetary scientist Daniel Cole of MIT, who, again, not involved in the study, but provides a good point of view as a planetary scientist. So as kind of how we see planet formation, hydrogen and helium are very, very low dense, very low molecular weight gases. And that means that you need a very strong gravitational attraction to keep these gases in the atmosphere. So if you're going to have a very strong gravitational attraction, you need a lot of mass. So that's why our gas giants have a lot of hydrogen and helium, because their cores were so big and had so much gravity that they kept the hydrogen and helium that was being formed and around them into their atmosphere. And so, as far as we know, life's not possible in a gas giant. So all that hydrogen, that 100% hydrogen, 100% helium mixture, 100% hydrogen, 100% helium atmospheres in the study, while life could replicate, probably not going to provide the conditions on the surface needed, right? What was in the broth. Also, if hydrogen is getting pumped into the atmosphere that much, that probably means there's high amounts of volcanic activity. So much so that would life even be possible? It may provide the foundation, but maybe not for a few millions to billions of years. Because hydrogen is so light, an atmosphere of all or mostly hydrogen would be puffier and extend up to 14 times farther from the surface than the Earth's nitrogen-dominated atmosphere. This means more starlight would filter through the atmosphere on its way to earthly telescopes, making it easier to probe those atmospheres for biosignatures. But at the same time, though, that means if you have all that hydrogen still maintained around the planet, and you extend the atmosphere, your planet needs strong surface gravity in order to have that atmosphere exist if it's not being constantly replenished by activity on the planet. So is life possible under that high strain of gravity? While the results also confirm the microbes could also live in helium and nitrogen-dominant atmospheres, these atmospheres would be thinner and therefore harder to detect around other planets. But again, then, well, could life even be possible to begin with on those planets? Like, they may be able to replicate in these atmospheres, but what's on the surface? You need a surface. Sager noted that the simple experiments might not be surprising to biologists. After all, there are microbes living in hydrogen-rich environments on Earth, such as niches in mines where calcium decay can create air pockets with 33 to 88% hydrogen by volume. Alright, so this could provide good insight on specific niches, but then not across the entire atmosphere. So life possible in certain locations. Also, both E. coli and yeast can survive without oxygen. E. coli can live in the guts of many animals, and yeast is used in the fermentation industry for brewing beer. But since neither microbe is adapted to a purely hydrogen environment, Seeger thought it was worth testing. Alright, so that's a good takeaway, is that they can replicate without oxygen, so they can undergo anaerobic respiration. They can create energy from food without oxygen. The problem with that, though, anaerobic respiration is incredibly inefficient and produces, like when they said brewing beer, alcohols that are dangerous. Eventually, yeast will die, either by heat and baking bread or in this process. So it's not sustainable to live off of that unless they've been evolved to only use that style of energy generation. We shouldn't limit or be too Earth-centric in what we consider interesting when we study other planets. Yes, that's due process, but at the same time, we have to understand the limits.